So, welcome everyone for a session Introduction to Natural Language Processing with Python spaCy, with presented by Nimrita Koul. So, Nimrita Koul is an associate professor of computer science and engineering. She is BE Computer Science and Engineering Gold Medalist, MTech Computer Science and Engineering Gold Medalist, and PhD Computer Science and Engineering. Nimrita has an academic experience of 16 years with many publications and one patent. Her research interests include machine learning and natural language processing. Nimrita is a senior member of IEEE and ACM and an international speaker on machine learning and data analysis. Okay, so over to you, Nimrita.
Thank you so much, Pooja. And hi, everyone. I'm pretty excited to be here today, and I'm looking forward to this session. I hope you all enjoy it and you find it useful, apply it to your projects, and build something interesting. So, shall we get started, Pujita?
Yes,
Yes.
sure.
Yeah, so the title of this session is Introduction to Natural Language Processing using spaCy. spaCy is a Python library, open source, free to download, and has a lot of built in functionality. It supports around 23 languages right now and has around 76 ready made pipelines which you can download and use. So, before we get started with spaCy, let's understand a bit about natural languages. Natural languages are those which we use for communication with one another. The humans use these languages like English, Hindi, or German. These languages are a bit difficult for computers to understand and respond to because of various complications, as we will see. So, natural language processing is a field of artificial intelligence which tries to build into computers the ability to understand certain commands in natural language and tries to build in the ability to respond to these commands also. So, the tasks which are generally involved in natural language processing are the tasks like identifying what do the words mean, are these words nouns or verbs, which word has a relationship or a bearing on which other word, what is the central idea or synopsis of the text given to us, or the tasks like analyzing sentiment of the text, whether the customer is writing something about the customer that has written about your product, is he happy or not happy about your product. What is the similarity in the two pieces of text? What is a document about? Is it a legal document, a political document, an entertainment document, things like that? So all these tasks form a core set of tasks which are generally involved in natural language processing. Now, spaCy is a library, a ready-made set of functionality which helps you to do all of this and apply these tasks to generate or to produce more interesting projects. spaCy is built in Python, and it can be extended with your own components and with your own trained models. You can as well use the built-in functionality, and that should also help you do a lot of stuff. Now, the important functionality that is already built into spaCy is a tokenization. It helps you to segment your text like paragraphs into constituent parts, sentences into words, punctuations, spaces, and so on. It helps you to identify the grammatical part of speech of each word or each token in your text, whether the word is a noun or a verb, which words are subject, which words are the objects of the in the sentence. It also helps you to identify the root words or lemmas for your words. It helps you identify the sentence boundaries. You can also use spaCy to identify the named entities. We will see that named entities are the real world objects which have a name in the real world, which also have corresponding representation in the text, either spoken text or written text. spaCy also has built-in functionality for you to disambiguate the meaning of the words according to the context. It can help you find the similarity between two pieces of text, two sentences, two documents. It helps you to classify your documents according to the categories, according to the main theme of which that document speaks. It helps you to identify and extract patterns from the text. It helps you to identify the text which satisfies certain patterns. You can, of course, use spaCy to train your own components for your custom tasks. You can save your spaCy projects. You can save your spaCy components and models using pickling, and you can load your saved projects from the disk. You can share them. You can package them into pipelines and share them with others to use. So spaCy, in addition to the core functionality, provides fully trained pipelines. Pipelines is a set of components, is a sequence of components which help you different tasks, which help you do different tasks on your text data. There are 76 trained pipelines as of now, and it works with 23 languages, including the common languages like English, German, French, Spanish, Arabic, and so on. So the first thing is to get your computer ready to work with spaCy, that is installing spaCy. I personally prefer to work with Anaconda distribution of Python. You may have a native installation of Python or an Anaconda distribution. On both Python distributions, you can have spaCy installed. Whether you're using pip to install on a native Python installation or you're using Conda, it's advised that you create a separate environment for spaCy. Creating an environment in spaCy is using VNV in Python. Once your environment is created, activate your environment, update your pip setup tools and wheels package, then use pip install spaCy to install the latest version of or latest stable version of spaCy. Once you have successfully installed spaCy, next thing you require to do is to download and install one of the trained models, one of the trained pipelines. There are many, as I said, there are 76 pipelines for you for 23 different languages. A pipeline looks, the name of a pipeline looks something like this, where these two characters en refer to the language of which this pipeline is. So this is an English language pipeline. Core and web are parts of the name. And SM here stands for the size. This is a small sized pipeline for English language. So what I'm trying to do here is I'm trying to use a spaCy download method, spaCy download function to install this a small sized pipeline for English language. So after these two steps, you are all set to import spaCy into your workspace and use its functionality. Suppose you are using Conda installation, then again, you need to first create an environment, activate that environment, then you can use Conda install IPY kernel to reflect the new environment into your Jupyter notebook. Once that is done, you can use Conda install spaCy. It downloads from the Conda Forge channel. Again, after your spaCy is installed, you are required to download and install a trained pipeline also. Again, in this case, we have downloaded the English pipeline, which is a small sized. Suppose you already have a spaCy installation, you can update it using -u, a flag to the pip install function. After your installation or update is done, you have to import spaCy into your pipeline. The common functionalities in a pipeline are tokenization. It can tokenize your text, it can split your text, it can identify or predict the parts of speech tags for your text, it can identify named entities, it can identify the dependency relationships between the tokens, between the words in your text. You can even use the component for matching certain patterns to your text. We will see the application of these functionalities as we go ahead. Here are some of the available pipelines for English. There is English small pipeline, which is around 12 MB. It has these components: token to vector, tagger, parser, sentencer, named entity recognizer, then attribute ruler, and lemmatizer. Of course, tokenizer is part of every pipeline. Then there is English pipeline, which is of medium size. MD here refers to the medium size pipeline. It is around 31 MB. There is a large sized English pipeline, which is around 382 MB. And then there is a transformer pipeline, which contains an implementation of Roberta based transformer. It is around 483 MB in size. Similarly, we have pipelines for German and so many other languages. Depending on what kind of functionality you require, you should install a correspondingly sized pipeline for that particular language. In this tutorial, we are only going to use the functionality which is available in the small sized English model. And for the training part, we will also use this medium sized pipeline. Once you have imported spaCy into your module, into your workspace, you can call spaCy.load function, and this helps you to load a trained pipeline into your workspace. spaCy.load creates a language object, and generally the name we give to this language object is NLP. It's much like we when we import pandas or NumPy, we use standard aliases for them, right? Import pandas SPD. Similarly, as a convention, the name we give to the language object, which is created by spaCy.load, is NLP. Let's have a bit of in-depth view into what a pipeline does and what does it look like. So as we saw, whenever we call spaCy.load and pass it the name of a trained pipeline, it creates a language object for us, which is called NLP. This NLP object consists of a sequence of components. Each of these components is capable of different kind of functionality. For example, the first component can tokenize your text. The next component can identify the part of speech tags. The third component can find the lemmas of your text, and so on. So this is a sequence of components, also sometimes called as a processing pipeline, right? Pipeline because there is a sequence of operations, one after the another, which are applied on your text data. So once this NLP object is applied on your text data, it creates an annotated document. Annotations means there are the text, there are the words, there are the tokens, as well as their lexical attributes, as well as their language specific information, which is called linguistic annotations. So here is what a pipeline generally looks like in spaCy. We pass in the text to the language object, which is called NLP. Here is the first part of the pipeline, is the first component. It's a tokenizer. It's followed by the POS tagger, then a general language parser or a dependency parser, named entity recognizer, and you can add your own components to this pipeline. So spaCy is quite extensible. You can add to the features if your specific project requires so. End of application of this pipeline to your text is a doc object, an annotated document object. So, what kind of linguistic annotations or linguistic information is provided by NLP? Is generally language specific, and it depends on the strength of pipeline that you have imported, whether the small pipeline or a medium sized pipeline or a transformer pipeline, and so on. So one more thing I would like to share here is that a species stores your data in the form of hash values in the doc object or in other objects, as we will see. It's not that if there are strings which are present in multiple documents, then those strings will not be stored again and again. Every unique string is hashed to a unique value, a numerical hash value, and it's stored only once. This saves space and also improves the performance of the models. So the first linguistic information or annotation that is present in the doc object, which is created by NLP pipeline, is tokenization. It breaks your text. So what we have done here is imported spaCy, loaded the small English trained pipeline. Here is a string which I have defined and stored in a variable called text. I'm applying this NLP model to the text, and it returns to me a doc object which contains not only the tokens of this text but also the annotations, the information which I may need for that text, for each token in that text. So here is a simple for loop by which we can print what are the different tokens in this text. Next piece of information which is associated by NLP object with our text is the POS, the part of speech for each token. You can access the value of part of speech of each token by the attribute called POS underscore. We need to associate an underscore with these attributes because the attribute values are also stored as hashes, right? So by attaching an underscore, we can see the string representations of those hash values. The next information or linguistic annotation that is created by NLP pipeline for your text is an entity name or entity label. It recognizes persons or companies or geographical locations or names of certain well-known books, and it associates a label with them that these are names of the people, these are names of the companies, and these are names of certain products, and so on. Next piece of information which is associated by NLP with your text is a word vector. We understand, I hope we understand that, obviously people who are not from the ML background will not understand this. But in general, ML models work with numerical data. So text data is not a very good input for these ML and DL models. So what happens is that your text data is first converted into numerical representations, which are called word embeddings or word vectors. These word vectors or word embeddings are also given to you when you download a trained pipeline of medium size or large size or transformer pipeline. These are not the part of small sized pipelines. So if you have downloaded a medium or large sized pipeline, you will also get the word vectors for all the common words in that particular language. You can access these word vectors by token.vector attribute. Now let's look at the main objects or main architecture of spaCy. spaCy has three main classes. The first is the language class, which is given to you in NLP object when you call spaCy.load. Second is a doc object, which contains the words as well as the annotations. The third important object is a vocab object. Vocab object is the vocabulary for spaCy. It contains the words from all the documents, and these words are stored in the form of hashes. And the subset or the object which stores these hashes and the words is known as string store. Every individual entry within the vocab object or within the vocabulary is known as a lexeme. Now, lexeme and token differ a little bit. While the token has linguistic annotations, lexeme does not. It contains the text of the word. It also contains the spelling related information, and it contains the information whether there is a capitalized character in the word or not. So, this information is independent of the context of the word, whereas the token contains the information which depends on context of that token as well. So here's the piece of code where we have imported spaCy, loaded the small sized English model. Then I have applied NLP on a small piece of text, I love coffee. Here I am looking up the word coffee in the vocabulary. Vocabulary can be accessed as doc.vocab.strings. And here's the output. This is the 64-bit string which represents the numerical value of hash of the word coffee. I can do a reverse lookup also in the same string store, which is accessed as doc.vocab.strings. I can pass the hash value and it prints back the string, which is corresponding to this hash value. So here's the diagram which showcases the architecture, the main classes, and the flow of information in spaCy. We start with the raw text, apply the NLP object to it. The NLP object applies the pipeline to the text. The first thing is tokenizer, followed by other components, lemmatizer, NER, and so on. Once this pipeline is applied to your text, a document object or a doc object is created. Subparts of this doc object are your tokens, and the spans. Spans are the sequences of tokens. Then you also have something called as docbin, which is a collection of spans. We have a class called example, which is used for training a component. If you desire to train a component with your specific data or fine tune some component. And then there is lexeme, which is like a token but minus the lexical information, minus the linguistic annotations. Besides these three objects, there also is, of course, we spoke about the token, the lexeme, and then there are objects like span group, docbin, and example, which are used when you are training your own specific components or fine-tuning the existing components. There are some other classes which are used for advanced functionality, a corpus class, a knowledge base class. Then there is a class which helps you do morphological analysis on your data, and so on. This is the pipeline which we already looked at. So it consists of a tokenizer, then a POS tagger, dependency parser, entity recognizer. There can be other components which are built into spaCy. There can also be addition of components which you have modeled or which you have designed of your own. There's also a functionality in spaCy which helps you to find out the text which matches the pattern. This pattern can be plain text, it can also be linguistic attributes. Find out the words which are nouns, find out the words which are spelled like a particular spelling, and so on. So you can write rule-based parsers in spaCy, and you can use these patterns or these rule-based matchers to extract a particular information for information retrieval from documents. spaCy allows you to serialize your models. It allows you to serialize your entire project or a specific component that you have fine-tuned and then share it with others. You can save them to disk. You can load them back from the disk and package them and distribute to others for use. The final functionality that spaCy provides is fine-tuning the components that are already present in spaCy. You can even create your own components, as we will see in the later part of this session. spaCy provides a pipe class in which you can use to create your own components and configure them, train them, and then share them with others. Also, when you download spaCy, when you install spaCy, you will see in your installation a folder called lang. In that lang folder, you have the rules and exceptions which are shared by many languages, right? A related group of languages. Within this module, you will also have a subset of modules, a subset of subdirectories which correspond to individual languages. For example, here you will see inside the lang folder, there's a folder called EN. You will also find the folders corresponding to other languages like German, Spanish, and so on. So you can install, now you can load individual language models like this, or you can load the models for the languages like we have already seen, like this English language small size model. So from here onwards, let's have a quick go through of how to actually implement all these functions that we learned about, all these components of the pipeline that we have seen. So we begin with the first step, that's importing your spaCy and printing what version of spaCy you have. I have version 3.3.1, and the recent release is 3.4 of spaCy. Then we are doing the next thing, which is to find out the tokens that spaCy has identified within the text, importing, loading your trained pipeline of small sized English language, declaring a bit of the text, hello, my name is Nimrita, applying this NLP object on your text and creating a document. This document consists of a set of tokens, which are nothing but the individual pieces of text, including the words and punctuations and spaces from the text that you have given as input to the NLP model. So here are the tokens that have been identified by spaCy from my text. Hello, comma, my name is Nimrita. Next thing is lemmatization. Lemmatization essentially means to identify the root word for the word in the text. For example, the word buy, bought, buying, buyer, all of these words have a common root like buy. You can identify these words using spaCy's lemmatizer, and you can access the lemma of every token using lemma underscore attribute. Similarly, you wish to find how the words are dependent on each other, how are they related to each other. That can be done by using the dp underscore attribute. It helps us see how two words are related to each other. Here's an example of a sentence. This time around, they are moving even faster. So what we see here is the output generated by the dependency parser of spaCy. It tells us that the word moving is the root, and the words like faster are qualifying moving, right? They are adverbs for the word moving. Even is the adverb for the word faster. Similarly, they and are somehow related. These arrows here are annotated by the exact dependency relationships between these words. And of course, we do not understand the meanings of these words. For that, spaCy provides us a very simple function called explain, spaCy.explain, and pass the name of these words, and it will tell you what is the full form of this word. For example, here it is an adverb modifier. This dot here is a punctuation. This is an auxiliary form of they, right? So we can use the attribute token dot dep underscore to find out the dependency of this token on other tokens in the same document. Here's an example where we see not only the text of the token, we also see its lemma, we also see its POS tag, we also see its dependencies, we also see shape of the tag. Shape of the tab token means what is the number of characters in the token, which characters are capitalized, which characters are not capitalized, the general form of the token. We will see whether that token is all alphabetical or not. We will see whether the token is a stop word or not. Stop words in any language are commonly appearing words, words like the, a, I, am, that. These words do not add much value to to the meaning of your sentence, and they're called stop words. So what I have here is the import of spaCy. Then I have loaded the small sized English pipeline. Here's a piece of text. Google Inc. is buying a UK company for $110 million. So I have applied NLP to this text and obtained a annotated document. Then what we are doing is for each token in this text, we are printing the token text. Token.text shows you the text of the token. Token.lemma underscore shows you the lemma of that token. Lemma means the root word. Then I can see the POS tag of that token. I can see the dependency of that token. I can see its shape. I can see whether it's an alphabet or not. I can see whether it's a stop word or not. So here's the output for this. It's a bit large in size. So I will reduce the size a little bit so that it fits in the screen. Here's the output. The first word or the first token is Google. The lemma is to Google. It's a proper noun. It is a compound word. The shape is like this. You can see that the first letter was capitalized, G was capital, so it looks like this. It is an alphabet. All the characters are alphabets. It's not a stop word. Ink again has all its linguistic annotations given to us. Let's look at is. So is a commonly appearing word. So we can see that stop word has a value of 1, which means is a stop word. Similarly, a here has a stop word value of 1, which means it is a stop word. You can see that for this dollar sign, the lemma is dollar and the POS is symbol. It is a symbol. It is a quantified quant mode. We'll see what quant mode means by using the explain function. So it's a modifier of a quantifier, right? Dollar is a modifier of a number of generally a sum of money. So it's a modifier of quantifier. In this way, spaCy allows you to see all the attributes of your text in addition to the text itself. And all these attributes are stored in your doc object as annotations of your individual tokens. Now we will see what are the named entities in the text. So I told you named entities are real world entities which have a name, like a person or a company or a country or a language, a religion, a religious group, things like that. So same, these two steps will be same in almost every program. You have to import and you have to load a specific trained language model and then apply NLP on some text. Doc.ents attribute helps you see all the named entities in that particular document. So doc is this annotated document produced by NLP. Its ents attribute contains all the entities that have been identified by spaCy in this document. So you can see ent.text, which means text of the entity, and label of that entity. What is the label or what kind of entity it is? So the first entity is Google Inc. You can see that it is an org, it's an organization. UK is a geographical location, so GPE, and 110 million dollars. This is money. The label associated with it is money. Next, we will see word vectors and how to use word vectors to identify similarity between tokens or between documents or between pieces of text. I spoke to you that for using word vectors, we need to have a medium-sized or a large-sized pipeline or a transformer pipeline. The word vectors do not ship with small-sized pipelines. For that reason, here I have loaded the medium-sized English pipeline, en underscore core underscore web underscore md. And here's the text, dog, cat, banana, and some random word. I have applied this NLP pipeline to this document. And for each token in that document, I am trying to print what is the text of the token. Does this have a vector? Which means that is the vector for this particular text available in the pipeline or not? So what is the reason behind having this has vector is that for common words in that particular language, the vectors are available. But for uncommon words or out of vocabulary words, like this, the vectors are not available. Vectors are not shipped in the pipeline. So has vector tells us whether the vector is present for that word, for that token or not. We can see the norm of the vector if it is available for that word, and we can also see whether that token is out of vocabulary. Out of vocabulary means not a common word, the word which is not generally used by the populace. Here we can print the word vector also. This is text one, which I used to create doc one. Here is another piece of text which I have used to create another annotated document called doc two. A third piece of text, a fourth piece of text. The purpose of creating multiple pieces of text and documents is to demonstrate the use of similarity also. So doc one contains dog, cat, and banana. And here text 4 and dog 4 also contains cat and banana. So it seems that they should be similar, right? They should have a high level of similarity. I have printed the similarity between doc 1 and doc 2. Doc 2 and doc 1 also contain dog and cat. Then doc 1 and doc 3, there are no common words. So as our intuition says, there should be less similarity between them. And there should be a high amount of similarity, high degree of similarity between text 1 and text 4, that is doc 1 and doc 4. Let us have a look at the output. Here is the first token, dog. It has a vector because it's a common English language word. Here's the norm of this vector, and it is not out of vocabulary, means it is a valid word in English. Here's a vector of this word dog. This vector contains numerical representations of not only the words, not only the alphabets, but also their meanings in the context of English language. Similarly, for the next word, for all the words, for the last word, we will see that the vector consists of all zeros. These all zeros signify that this word here is not a very valid word. It's not a valid word. It does not have a vector because it is not a valid word, and it is an out of vocabulary word. See, the attribute OOV is shown to be true. Now we'll see the values of similarity. Doc1 and Doc2 both contain the words dog and cat, so they have a high degree of similarity. 1 and 3 had no common words, so the similarity is very less. Doc1 and 4 had very similar words like dog and cat in both, so the similarity is pretty high, 0.96. So the range of similarity values is between 0 and 1. Next, we will see how to clean our text or pre-process our text using spaCy. So cleaning means generally removing the words which are redundant, which do not add value to the meaning of the text, like the stop words or the punctuation marks, or words like etc., 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 that is written as IE and so on. So these words like etc and IE are identified by a special value of POS tag, which is equal to capital X. So whenever the attribute POS underscore for a token is X, it means this is a junk word or a slang word and it can be removed. So here we have imported spaCy, we have loaded the small English language model. Here is a piece of text that I'm going to use as input to NLP, create the doc object, and then I have printed the original document. I have found what is the total number of tokens in the original document. Len attribute can give you this. Len function applied on doc can tell you how many total tokens are there. Now we will pre-process this document. We will identify which tokens have a value of X, which of the tokens are stop words, which are the punctuation marks, and then we will filter them out. We will drop them. So here is the code which does it for us. Cleaned doc contains a list of tokens if that token does not have POS underscore value of capital X, and that token is not a stop word, and that token is not punctuation. So clean doc contains only those tokens which are not pos underscore is equal to X, which are not stop words, and which are not punctuation marks. So this list has been stored in clean underscore doc. We can print it. We can print the number of tokens now in the clean doc. And for each of the tokens in the clean doc, we can print the POS value. So we have total 7 tokens now remained after cleaning. 26 is a number, books is a noun, dollar is a symbol, 10.5 is a number, plus is a conjunction, and so on. Next, we identify numbers, percentages, email addresses, and URLs from the text. So again, you have to repeat the first 2 steps of importing and loading a model, defining some text on which you can do the processing. This can be defined in line like this, or you can also have it in a text file or another kind of file. Apply NLP model on your text. Then in a for loop, for every token, we are going to make this check. If the token is like a number, then you have identified a number, right? Simple. So far, it is simple. You have identified a number. But if you want to identify a number which is a percentage, then you also are looking for next token, which should be a percentage sign. So for going to next token, you are going to token.I plus one. Token.I is the index of the token in the document, and you're going to next token. Next token should be a percentage sign. If you find a percentage sign next to a number, which means the number is a percentage number. Similarly, if you have to identify an email address, you can simply check for the linguistic attribute like email. If this returns a true, that means you found an email address. There's an attribute called like URL. Again, if it returns true, which means that the identified token is a URL. So from this text, we have a number which is 2020. Here we have a number which is 10, and 10 is also a percentage number here. We also have an email address here, and we have a URL which is identified here. So we did not have to do any manual processing here. All of this could be very easily done because of the built-in attributes of your tokens inside the doc object. Named entity recognition and identifying which are the entities present in the text can be done very easily using spaCy as well. First, let's have a look at all the entities that spaCy can recognize. You can do that by using the getPipe function. So NLP objects getPipe function, you just pass it the name of NER or entity recognizer. You'll see all the labels of valid entities that a spaCy recognizes. You can extend the named entity recognizer and help it recognize the entities like gadgets, iPhones, dates, or events like which are specific to your particular geographical area, and that can be done. Save those components and share them and reuse them. So here in this code, we are trying to identify all the people, all the companies, and all the languages, the entities for organizations, for people, and the languages. Here's a piece of text. You can see that there are company names like Google, Samsung, Microsoft. There's the name of a person, the names of two languages. So we create the text, process this text using NLP object. For all the entities present here, you use doc.ents attribute, and then we are identifying individual entities. Wherever the entity label is organization, that entity is a company name. Wherever the entity label is a person, that entity is a human being, that's a person with a name. And similarly, we are identifying the languages. The general syntax is same for each entity in doc.ents. If the entity label underscore is equal to person, then print out that person, right? Print out the name of the person. So here is the output. These are all the entities identified in your doc. These are all the companies that have been identified: Google, Microsoft, Walmart, and Samsung. Here are all the people. John has been identified as a person. And here are all the languages in the text: Mandarin and Arabic. Now, this can be used to apply privacy to certain piece of text. Suppose you do not want people to know what are the names of persons referred to in the text, what are the companies, or what are the events or dates mentioned. You can use masking. So how do we do that? Here's a piece of text. Hi, my name is Dr. John. I live in Italy. I work at Google and this and that. So you pass this text to NLP, and then we want to mask out. We want to replace these personal pieces of information by something which is not so identifiable. So we can do that by first finding out whether the entity type of a particular token is person, or the entity type of a particular token is an organization or a geographical location, or whether that token is like a number or like an email. In all these cases, we want to set the entity type for that token to be unknown. We want to replace that token to be unknown. Here in the function called mask data, we are applying this find personal data function to every token inside the document and replacing that token by the word unknown in case that token's entity type is a person or an organization or a geographical location, or that token looks like a number or it looks like an email address. So here is the final output. Here was my original text, which contained all the personal information. Here are the numerical labels that spaCy internally assigns to different kinds of entities. Here is my final processed text where the personal information like name and company and phone number have been masked. They have been replaced by a word called unknown. Now, spaCy has a very beautiful visualizers built into it. Two visualizers are present as core parts of spaCy. One is displaycy and other is displaycy ENT. First one helps you to visualize the dependencies in your text in the form of a graph like this. Then the other visualizer, displaycy ENT, helps you tag the entities within your text, right? So Sebastian Thuren has been identified and labeled as a person. Google Inc. has been labeled as an organization. This as a date, and Mandarin as a language. There's a very simple syntax to it. From spaCy import displaycy. Displaycy is the visualizer. You can call displaycy.render or displaycy.serve to visualize the type of relationship you want to visualize, either an entity or a dependency. So here's a simple example where we are training a named entity recognizer to identify a new entity besides all the entities that spaCy knows. Here we are training it to recognize a new entity called an iPhone. So, for training a component using machine learning, we need to provide input data. This data is divided into two parts: a training data set and a testing data set, or an evaluation data set. So here is our input file in which there are 6 lines of text. Every line of this text will be will be converted into a separate document. We will treat iPhone as an entity. We will make this program in such a way that iPhone is considered as an entity, and rest of the text is taken as the content of the document. So this input file is in the form of JSON, and it is located here. It's shipped as a part of spaCy's core course, which is available at spaCy.io. This requires us to import JSON in addition to the normal spaCy modules, and we will also import span, matcher, and docbin because we are training a module, so we require the examples to be shaped in the form of a docbin. We will use matcher in order to identify the pattern which resembles iPhone X or iPhone 11 or iPhone 8, iPhone followed by a number, or generally iPhone followed by X. So we will first read the testing file. We will read the JSON file, which contains all the text lines. We will import an EN model. This is a blank model, which means it only contains the tokenizer, not the remaining components. You can load it with spaCy.blank. You apply matcher on it. Matcher object helps you to create a matcher which can be passed patterns which you want to identify in your text. Since there's a shortage of time, I'm not going to depth of how to apply patterns, but in short, it helps you to identify all the text in your document which matches a specific pattern or which has specific lexical attributes. So we create our document from the text file, from the JSON file, identify the entities in it, and then we can split it into training part and the development part, or the validation part. We need to convert our training data into a specific format which is called a docpin. This docpin has to be created both for training and validation set. Then we use spaCy init config command to configure the training attributes. Then we train our model, and the Python spaCy train function helps you to train your model and store the best model in a folder that you specify in this command. You can train your model. It goes on like this. The best trained model is stored for you. This best trained model can be then downloaded, just like we used spaCy.load to get trained models for us. We can use spaCy.load to get the model you just trained for yourself, and then you can apply this model you have just created on the document, just like we apply the pre-trained models. So this is something you have done from scratch on your own. This model can now identify iPhone as an entity, right, which is not the functionality present in spaCy as such. This model which you have created can also be packaged and shipped to others for use. You can also make your model a part of spaCy's next release if this is really good, if it passes the evaluation. So this is very quick tour of spaCy that I provided in this session. You can explore it further, and you can build very interesting projects of your own, like a funny chatbot or an interesting entity recognizer for the language that you speak or that you are interested in. It's 9:04. Uh, Maybe a few questions because we have time up to 9:10, right, Pooja? Pujita?
Yes, yes, Nimrita. It was a fantastic talk, and our attendees are also really loving it.
Thank you
It was
so
so
much.
well organized. I mean, it was such an information in a very organized manner.
Thank you
Thank you
so
so
much.
much for presenting. Yes, we have a few questions. So, since we are, a little out of past, out of time, so I'm just going over the questions quickly. So,
Yes.
first is why UK shows is alphabet equals zero. So, I think in your code somewhere earlier you have showed this that UK
Yes,
is
yes.
alphabet is equal to zero. So, the person
Right.
is
So
asking
U
why.
dot K dot, right? The dot
Yes,
is
U
not
dot
treated
K
as
dot.
an alphabet, right? So if your entire token consists of only alphabets, it will have the annotation of is alphabet is equal to one. Since there is a dot, it doesn't. It's not treated as an alphabet.
Okay, awesome. There's another question. Does spaCy have something similar to NLTK collocations,
Yes,
where
yes.
you can get likelihood ratios of the word occurring before the word in question?
Yeah, that's a very interesting question. In fact, spaCy is not meant to take the role of NLTK. NLTK is a research package. It allows you to see the probabilities. It allows you to apply the Bayesian rules on your text data. spaCy does not allow it as such, right? It's a package which is meant for production level use, where you apply the built-in functionality or built on top of that functionality without doing the inner probability related computations or even seeing them.
Okay, thank you for explaining that. There's another question from one of the attendees who's asking that how to tackle cases where there is a mix of languages in the same text.
For the mix of languages, you can always go and train your own component, right? Your training data determines what your component learns. If you show your component the training input data, which is a mix of languages, then of course it will learn the mappings between those languages. Of course, it will treat all the input you give as ASCII or as Unicode.
Okay, thank you so much for explaining that. We have just got another question from one of the attendees who's asking that, can you tell us about the most exciting project you applied spaCy in? And by the way, your presentation has been amazing.
Thank you so much. Yeah, so I'm working on Sanskrit, and spaCy does not support Sanskrit as of now. So what I am actually building is I'm building a translation system using the components provided by spaCy. I'm recognizing the entities in Sanskrit text. Again, somebody asked right now about the mixture of languages, right? It's
Yes.
somewhat like that, but not exactly a mixture. I'm using specific languages like German and Arabic, and I am importing the functionality from Arabic and German and trying to apply it to the Sanskrit for identifying those entities and dependency parse values between these tokens in Sanskrit.
Oh, that's amazing. That sounds really interesting. I think that's all the questions we have. We can have like 2 more minutes if anyone wants to
Yeah, I can
ask
see
it.
that a couple of people have asked about the link to
Yes.
the notebook. The link to the notebook is here on my GitHub. Here.
Yes, I
If you
think
if you
someone,
if you just go to my GitHub, you'll find it's a public repository. You can find it there.
yeah, I posted the link of GitHub, I think, in the chat. Everyone might have got it. Okay, so there's another question that do you have any recommendations when working with word embeddings with large models? Are there any resources for advanced applications using spaCy or any utilities?
Yes, there is word2vec, which is generally used by researchers, right? But spaCy provides talk2vec, which is, I'm not experiment with that as yet, but it is said to be more compact and it uses aspect-based conversion. So I would suggest that you explore that how does the talk2vec compare with respect to the sizes of word vectors as generated by word2vec. That is one direction in which you can proceed and explore.
Okay, that's a great suggestion. I
So,
think we,
in the chat, shall I post the link to this notebook?
yeah, sure.
Yeah, I've done that.
Yeah, thank you so much for that.
Thank you so much, Pujita. You have been a great host. And thank you, everybody. It has been a wonderful session for me also. Thank you so
Yeah,
much.
thank you so much.
Thank you.
We have just got another question. So someone is saying that thanks. I would be interested in to see growth models in the future. I think that's not the question, but yeah, thank you so much,
Thank you
Nimrita.
so much. Thank you so much, Pujita. Thank you, everyone, for joining this session.
And yes,
Have a
Nimrita
great
has
time.
also posted her LinkedIn. So anybody who's interested to know more or connecting with her, please feel free to join.
Thank you so much, everyone, for joining. Thank you so much for being with me. Please feel free to connect with me on LinkedIn or, DM me in case you need further help or any further resources for spaCy or NLTK also. Thank you so much.
Okay. Thank you so much, Nimrita, and
Thank
thank
you
you
so much.
everyone for
Thank you.
joining.